to repulsion at very close distances. Okay. And then there will be an attractive part which is below 0. Okay. Followed by again rise in potential level. Still attractive, but to higher energy. Typically, this is how it looks like. Okay. But you can have in principle systems. You can have very ordered lattices without having necessarily attractive forces. Even with purely repulsive forces, you can have an ordered lattice. By virtue of confining the repelling particles within the system, okay, you forcibly have this called a hard sphere attraction. In that case, I hope I don't mention too much into the physicist language. Hard sphere will be, there will be a repulsion almost coming from infinity. Okay. And then flat 0. Okay. There is no other. The only interaction is infinite repulsive interaction. As long as the two particles, one particle is 0 and another particle at some distance r, at far distances they don't feel the presence of each other. But when you bring it close, suddenly it finds a home. But in this case, you can have some ordered structure. Just think about it. I'll come to this maybe after some time. But potential energy is by and large directly this. Kinetic energy is related to the temperature at which you are keeping the system. And it's this competition between this which is going to decide the state of matter. Okay. So this is one language in which many physical properties and like structure or transport properties are discussed. Okay. The other language is the language of symmetry, which is very helpful and very related to, for instance, the structural properties. So what can we tell about the symmetry of the states? And since this is getting too cluttered, I won't maybe
you should not don't erase the phase diagram.
I'm not going to erase the phase diagram. I'm only going to erase this potential will be a CO2 thing which I want. Yeah, now let us talk about the symmetry relationships, for instance. So which of these spaces is most symmetric? Let us say, take case of ice again. Just imagine you're seeing ice and water and steam and all that. Okay. So you have ice, water and steam. Okay. Which of these three states or three phases of water, okay, which of these is the most symmetric? Yeah? Solid. You mean to say, let's just solid, liquid, and gas. And why do you think you say let us arrange them in the order of increasing symmetry? So you mean to say this is top in symmetry, solid, and which what is the next lower symmetry one between liquid and the gas? Both are same. What is it? Liquid is more symmetric than gas. Liquid answer is different. Okay. So I will say symmetry is highest. Okay. What? Like any other physicist, I always run out of symbols to describe what is happening in the mind. Okay, I'll put a big arrow here. This is the most symmetric. This is, should we call it medium symmetric? Okay. What about gas? Is the lowest? Why do you think so?
Actually, you have to look at the time scale of observation. It's a pretty long time scale.
Yeah.
And the average.
Right. No, I'm coming to that. I just want them to justify they have certain thought process in mind. I want them to justify. So, whomsoever told solid or ice is the most symmetric in the case of water. Obviously, when you make a statement, you also have to defend it. Right? Why do you feel? just feel free to talk about. I mean, I also learned it that way only. Okay. Maybe right, may not be right, but nothing wrong in adding our thoughts. Yeah.
Okay.
One second. Yeah.
But gas and liquid would have a shape of their own.
Yeah.
So how do we define symmetry without shape?
I will make a counter statement again. Just because they don't have a shape of their own, I'm just using your own language. Okay. I will tell that they are the most symmetric objects.
Right. So,
in fact, I will say gas is much more symmetric than the liquid, which in turn is much more symmetric than, say, crystalline mass.
see
Yeah.
there was a one
That's
small
why we put it in
point to make. The way you define symmetry is if it remains invariant with respect to some operation, rigid motion.
You are a physics student?
Yeah, maths, physics.
Okay, maths physics, fine, right.
So,
Good, I will translate thing.
So if under that rigid motion, if something remains invariant, then it is symmetric.
Right.
In that case, if there is some long range order in some, if something looks more ordered like solid, if you tend to move it here and there, it won't remain the same. But gas, it's all random. So even if you move it, it's just going to remain the same. So hence more symmetric.
Beautiful. So I will put it in simple words. Okay. Let us take the instance of say solid and more specifically let us say ice. Okay. Let us say one dimensional ice. Okay. I am also going to approximate all this H2O with one spherical block. Okay. Let us say these are all arranged in a nice periodic arrangement in a crystal. Let's say some space in here. Okay. This has, as this says, this has lower symmetry than the other phases. Okay, because like ice, if you take, okay, if you start from this point, if you translate by exactly say one periodic space, lattice spacing it is called, one periodic entity, whatever it is. In real space, it is a lattice spacing. Then you end up with the same objects. Okay. But if you want to arbitrarily translate to say some point here, okay, you find that the environment around this is not the same like what you have here. Okay. In other words, you take the case of say a liquid or even a gas, for instance. Okay, you have a disordered, completely random arrangement of atoms and molecules. Okay. What I will do is, let us say you sit on one atom or molecule, okay? Then you close your eyes, and then you move around your liquid or gas in all possible random translations and reflections and whatnot, rotations. You do all possible operations and keeping your eyes closed. Then you open your eyes. You will find that nothing has changed. Everything remains identical. Okay, I will say okay, it has infinite degrees of symmetry. Okay, it is uncountable number of translational, rotational, and inversion and mirror symmetries. Oh, name the symmetry element, everything is there. Okay, whereas it's not the case in the case of such discrete entities as a lattice. Okay, it's one common misconception